So welcome to Chapter 8, Part 1. In this chapter, we're going to be looking at solutions and their concentrations. We're going to be doing some calculations around molarity and figuring out what a dilution is and how to calculate it. We're also going to be taking another pass towards stoichiometry, which is that mole-to-mole conversion. Or in this case, we could even do a volume-to-volume conversion, and there's a reason for that. We're going to be looking at aqueous solutions, electrolytes, and non-electrolytes. And then we're going to be learning about precipitation reactions. Actually, we've already learned quite a bit about these and how to express those in equations. And we're going to do our introductory little bit regarding acids and bases. So let's get started. Now, in order to talk intelligently about solutions, the first thing we need to be able to do is identify the parts of the solution. So the thing that you have the least amount of is going to be called the solute. So the solute is the minor component. The thing that you have the most of is the solvent. The solvent is going to be your major component. So let's say that we had some sodium chloride, that is table salt, and we dropped it into some water. We would in short have a solution of sodium chloride or salt water or saline. And the solute would be the sodium and the chloride ions because they separate once they get into water. And the solvent would be the water. And together they create what's known as a solution. Now we could give it some fancy language and call it a homogeneous or homogeneous solution or a mixture, which basically means that when you look at it, you're not going to see any of the solutes clustered together anywhere. So homogeneous means that they're equally distributed throughout the solution. Your solutes are equally distributed throughout the solvent, and you have a nice homogeneous, ubiquitous distribution of stuff. So when we talk about our solutions, one of the things, or possibly the thing that we really want to know is how much solvent and how much solute do we actually have in our container? And what sort of ratio are they coming in at? And as a result, we have a couple of ways of describing this information. One of them is to say that we have a dilute solution, which is when we have a small amount of solute compared to the amount of solvent. The other way is to say that we have a concentrated solution, which means that we have a large amount of solute compared to the solvent. So these are probably fairly intuitive concepts. Most of us have an understanding of when things are diluted and when things are concentrated. But how do we actually apply numbers to this? How do we quantitatively describe this? Well, that's going to get into our next bit talking about concentrations, which is actually looking at molarity and the like. So let's get on to that. So how do we describe a solution? Well, as we just said, we can take a look at the concentration, and we know that it has to do with how much solvent we have and also how much solute has been added to that solvent. Now there's two ways to discuss this concentration besides concentrated and dilute. We could measure this with a term known as molarity, and the other way we can look at it is through what's known as a dilution, which is a calculation. So let's take a look at both of those. So in the chemistry lab, a common way to talk about solution concentration is with molarity. Molarity is abbreviated with the big M as opposed to the little m, which is molar. So molarity, and molarity is the amount of solute in moles divided by the volume of the solution, which is the amount of solution in liters. So we could say molarity big M is equal to the amount of solute, which is moles, over liters. And you'll want to have it in liters. I believe that's fairly standard, as opposed to milliliters, I guess, is what I need to add on to that. So it's moles per liters. So while we're here looking at this slide, what do you notice about molarity? Well, we've got a term that has two different types of units in it, a mole and a liter. One is the measurement of the number of particles. The other one is the measurement of volume. When you have values like this or expressions like this, what are we going to be able to use those for when we do calculations? A conversion factor. Yes, we're going to be looking at molarity as a conversion factor. So it would behoove you to write it down or memorize it somehow, reserve a brain cell that says molarity, find it here, and make sure that you understand that molarity is the concentration of moles per liter. So yes, we can use molarity in calculations as a conversion factor. So let's say that we had a 0.500 molarity of sodium chloride in our solution. We could say that what it contains is 0.500 moles of sodium chloride for every 1 liter of solution, and we could write it in a conversion factor such as what we see here in the first position, in which we could convert liters into moles. Or we could flip it around, because that's what we can do with conversion factors, wherein we could take moles and then convert it into liters. You think we'll be doing that sort of stuff? You betcha. And we're going to start by using our molarity right here in an example. So let's say that you dissolve 25.5 grams of potassium bromide in enough water to make 1.75 liters of solution. What is the molarity of the solution? Well, we need to put our terms in moles and in liters. Right now what we have are grams and liters. So let's make a note of what it is that we're given. So we're given grams of potassium bromide and 1.75 liters of solution. So we can use the 1.75 liters of solution. What we can't use is that 25.5 grams of potassium bromide. We need to get out of grams of potassium bromide and actually into moles of potassium bromide. So what we need to do is set up a solutions map. I like to come up with an idea, because remember, when you're working dimensional analysis, and this is a dimensional analysis problem, you want to arrange your units and then just let the numbers go along for the ride. So the thing that we need to do first of all is we need to get out of grams of potassium bromide and into moles of potassium bromide. And the way that we do that is through, guess what? Another conversion factor, molar mass. So if we can figure out the molar mass of potassium bromide, we can create a conversion factor that gets us out of grams of potassium bromide and into moles of potassium bromide. And once we have the moles of potassium bromide, we can just simply put moles of potassium bromide over liters of solution and figure out what the molarity is. Okay, so let's start doing some math. So one of the things we're going to have to do, well, the first thing we're going to have to do is actually come up with the molar mass of our potassium bromide. So how do we calculate that? Well, if you said to yourself, well, I'm going to go to the periodic table, look up the molar mass of potassium and look up the molar mass of bromide and add them together, then you would be correct. And when we do that, we end up with 119 grams per mole. So this is going to be our conversion factor to get us out of that 25.5 grams of potassium bromide and into moles of potassium bromide. So we're going to set that up into an equation. So we're going to take what we're given, which is our 25.5 grams of potassium bromide. And we're going to plug in our conversion factor, which is our molar mass of potassium bromide. And remember, when you're setting up your conversion factor, the units that you seek go on top. And the units that we seek are moles of potassium bromide. We're given units of 25.5 grams. So we're going to put our moles on top in our conversion factor. The grams will therefore be on the bottom, which means that we can eliminate grams because it's a repeating term, shows up in the denominator and the numerator. And now we just get to do the math, which means we're going to divide 25.5 by 119, and we'll end up with 0.21429 moles of potassium bromide. Now what are we going to do with this value? Well, when it comes to molarity, what we're looking for is moles per liter. So we're going to actually drop both of the numbers in the equation together. So we're going to take our 0.21429 moles of potassium bromide, and we're going to divide it by 1.75 liters. And that's going to leave us with a certain amount of moles per liter. And we end up with 0.122 moles. And of course, you can do a check to figure out if that's correct. And here you can kind of figure it out. And off we go. Remember back in the day when we used to come into lab and there would be all of those chemicals set out for you, and you would look at the labels and you would wonder, what the heck any of that meant, and you would see things like 0.15 capital M NaCl and stuff like that. Well, those were all solutions, dilutions that were made from a stock solution. Those were things that I made up, mixed up for you guys back in the workroom. And I used this math right here in order to do that. So what you were working with was what's called a dilution. Now, a dilution is when a new solution is prepared from a stock solution. And your stock solutions are typically a concentrated solution of your solute. And you start off with a stock solution because you can always water it down, that is, dilute it, and make something that is useful in your lab to do your experiments. So the way that you make solutions is that you have to figure out what the concentration of your stock is and how much of a concentration of your solution that you want to make, and do the math that way. And I know that sounds kind of esoteric. We'll look at an example to see how that goes. But basically what we see here is that C1 times V1 is equal to C2 times V2. Well, what do the C and the V mean? Well, C means the concentration. The concentration of one solution times the volume of that solution should be equal to the concentration of your second solution times the volume of that second solution. So, for example, when I wanted to make a solution of 0.1 molar sodium chloride, and maybe I wanted to make, like, I don't know, half a liter of it, I would take half a liter and my concentration, which would be 0.1 molar, and then I would go to my stock solution, which came in at a particular concentration, I don't know, let's say something like 3 molar, then I could do the calculation, because I have 3 of the 4 values, and just manipulate the numbers and come up with how much of the stock I needed in order to make the solution for you to do your experiment in lab. Now, if you look down here at the bottom, it says the mathematical relationship is concentration times volume. And it doesn't really matter what sort of concentration unit you use. You could use something as molarity. You could use some other value if you wanted to. As long as you're converting from between the same types of concentration units, it doesn't really matter what it is that you use. Again, it's basically a ratio that we're looking for here, and it's going to mathematically work out the same way regardless of what these units are. So let's take a look at an example 8.3. So they're asking us to what volume should you dilute a 0.2 liter of a 15 molar sodium hydroxide solution to obtain a 3 molar sodium hydroxide solution. All right, so let's see what we have here. Well, if we take a look, we see that we have a liter and a molarity. So we have a liter and a concentration, which means that we're looking at a dilution equation. So what we're given is a volume, an initial volume, an initial concentration, and we're given a final concentration, and what we need to find is the final volume. That's what we're missing. So the equation that we're going to end up using is going to involve all 4 of these. So we have to put all 4 of them together, and what we're going to be using is that dilution's solution formula, which is M1 times V1 is going to be equal to M2 times V2. Our M could be a C, it doesn't really matter. I tend to use C, but it doesn't really matter as long as we're using a concentration, and our molarity is a concentration. So we need to set up this equation so that we can solve for V2. All right, so the way that we're going to do that is we're going to take our initial equation, and what we need to do is isolate V2. So if we divide both sides by M2, that will allow us to have V2 on one side of the equation, and we would have M1 times V1 over M2. Now in this example, they just switched sides, but it's still the same information. So now we can plug in the values for M1, V1, and M2. So you can see here our initial concentration was 15 moles per liter, and we have a volume of 0.2 liters. And what we want to end up with is, and then we divide by 3, molarity, and what we want to end up with is a volume. So if we get rid of moles per liter or moles per liter, what we end up with is liters, which is good. The units that we're left with is liters because the units that we're looking for are going to be in liters. That's what a volume is. So once we do the math, we can see we're going to come up with 1 liter. So what we need is 1 liter in order to satisfy our requirement. So the final units in liters are correct, and you could run these numbers in a different way to double check just to make sure. So that's how those are done. So yeah, this is what I frequently did. It's just like I'd read what we need and pull out my stock solution, and I believe I did have some 15 molar sodium hydroxide, and would whip that stuff up and by using this equation right here. So yeah, that's how you do that. So you might remember when I first introduced the concept of molarity just a few slides ago, I said that it can be used as a conversion factor. And we are going to be using it as a conversion factor because it does bring together an equivalence between 2 different types of units, the moles and the liter. We can further use our molarity when we're doing stoichiometry problems. Now you might remember that stoichiometry problems are a mole to mole conversion or a gram to gram conversion, and what's different in our conversion is that we're going from one substance to another substance, and we know that relationship exists by looking at a balanced chemical equation. So that is stoichiometry. The bulk of this slide is going to show you how you can use volume and molarity to calculate moles. You can also use molarity and moles to calculate volume. And depending upon what your question is asking you with regard to stoichiometry, it will likely either ask you to convert to moles given a volume and a balanced equation, or it'll ask, or the opposite of that. So I know I've totally butchered this slide, but I've recorded it 4 times, and 4 is my limit. So you get what you get with this slide. So let's put this concept of solution stoichiometry to the test. So we have this balanced equation where we have 2 potassium bromides interacting with calcium hydroxide, and we get 2 potassium hydroxides and a calcium bromide. Now what we're being asked is this: if we have a 0.225 liters of a 0.750 molarity potassium bromide solution reacting with a 0.300 molarity calcium hydroxide solution, how many liters of calcium hydroxide were used? So let's see what we have. The first thing that we know is that we're given the molarity of potassium bromide, and we can just go ahead and convert that into moles per liter. So we have 0.750 moles per liter of potassium bromide. We also have the molarity of our calcium hydroxide, which is 0.300 molarity, or 0.300 moles per liter of calcium hydroxide. The other bit of information that we're given is that in this equation we used 0.225 liters of potassium bromide. And what we're being asked is how many liters of calcium hydroxide were utilized to interact with our 0.225 liters of potassium bromide. Now, as we're thinking about how to set this equation up, keep in mind that these 2 pieces of information up here are going to be utilized as conversion factors. So what is going to be our solution's path here? Well, if we take what we have from our givens, we like to start with a known value, and the known value that we're going to start with is going to be the volume of our potassium bromide. So you might be asking yourself, well, why wouldn't I start with the molarity? Well, you're not going to use molarity for anything other than converting from moles to liters or liters to moles. And the only value that we're given where we have just 1 unit, not 2 units, 1 unit, that's going to be the liters of potassium bromide. So we're going to start with our volume of potassium bromide. Now with the molarity of potassium bromide, we can convert that into moles of potassium bromide. And with our balanced equation, which were given at the very beginning of this slide, we can go from moles of potassium bromide into moles of calcium hydroxide. And then with the molarity of calcium hydroxide, we can go from moles of calcium hydroxide into the liters of calcium hydroxide. So to drop all of this in, if we start with the liters of potassium bromide, we use the molarity of potassium bromide to convert to moles of potassium bromide, and then use our equation in order to get a conversion factor, a mole-to-mole conversion factor between calcium hydroxide and potassium bromide. That will allow us to come up with the moles of calcium hydroxide, and then we can use the molarity of our calcium hydroxide to get us into the volume of calcium hydroxide. So if we take all of this and drop it into an equation, we would start with our volume of potassium bromide. We would use the molarity to do a conversion factor, and that would allow us to get out of liters of potassium bromide and into moles of potassium bromide. We can next drop in the conversion factor that we get from our balanced equation. This is the stoichiometry part right here. And that will get us out of moles of potassium bromide and into moles of calcium hydroxide. But we don't want to be in moles of calcium hydroxide, so we're going to drop in the molarity of calcium hydroxide. That gets us out of moles of calcium hydroxide and will leave us with the units of liters of calcium hydroxide. And that will allow us to answer the question of how much calcium hydroxide was used in the chemical reaction given what we started with as far as potassium bromide. And we run the numbers and we see that we've used 0.281 liters of calcium hydroxide. So how do substances actually dissolve in water? How do they become aqueous? Well, if we consider two very familiar substances, that is salt and sugar, in water, this will give us a really good example of what's happening with most of our compounds. Now, salt water is an homogeneous mixture of the ions of sodium chloride and water. And sugar is going to be a homogeneous mixture of the molecules of sugar and water. So how is it that these solids are going to dissolve in water? Well, let's just take a look and see. So first of all, we need to understand the nature of water. And we've actually studied water a little bit. The thing about water is that it has a lot of forces in it, because remember, water has a polarity. And when you drop a solute into water, the forces of the solute, because very likely they will have forces of themselves, are going to have some sort of an attractive force between the molecules of the solvent. So that when we mix the solute and the solvent, the attractive forces between the two are going to allow the solute to be incorporated into the solvent, provided that the attractions between the two are strong enough. So, as I stated a moment ago, water has this uneven distribution of electrons within each water molecule, so that you end up having a region that has a negative charge and a region that has a positive charge. Now, if you were to drop in a solute that has a positive charge to it or a negative charge to it, or an area where its molecule has a positive region and a negative region, those forces very likely could interact with those positive and negative charges that we see around a water molecule. And in fact, that does seem to be what's happening when we look at substances like salt and sugar dissolving in water. So let's say that we were to take sodium hydroxide and put it into water. One of the things that's going to happen is that the ions are actually going to separate, and they're going to be surrounded by water molecules. Now, let's just look at sodium, for example. Sodium is a positively charged element, or ion rather. And what it's going to do in water, the reaction that it's going to have, is that water is going to be attracted to it, but it's going to be the negative area of water that will be attracted to our sodium ion. So the water molecules will orient themselves so that the negative region of their molecule is pointing towards the sodium ion. Well, what's going to happen with the chlorine ion, that chloride? Well, it's negatively charged, so what do you think is going to happen? The water molecules are going to flip around so that the positive region of the water molecule is facing the chloride. And in this way, we see the ions of sodium chloride being integrated and, quote, dissolved in water. So each ion is attracted to the surrounding water molecules. It gets pulled away from the crystal itself. So we see that separation of the ions. And when it enters the solution, the ion will be surrounded by water molecules, and the water molecules are going to act as an insulator from all the other ions that accompanied the sodium and the chloride into the water. And as a result, the solution, within the solution, these ions are going to freely move around the charged particles, and water will accommodate them because water can either accommodate a positive charge or a negative charge. Well, that's all great and all about salt, but what about sugar? Well, the good news is sugar does not break apart once you put it into water, which is why our coffee tastes so good when you add a little sugar to it. It doesn't turn into carbon and hydrogen and oxygen. So it stays the sugar molecule. So what happens then if sugar's not breaking apart like sodium? What's happening then that allows it to incorporate into water? Well, a sugar molecule is made up of carbon, hydrogen, and oxygen. And those oxygens are going to create areas of polarity over the area of the sugar molecule. So that when we drop sugar into water, the water molecules are going to flip around so that the positive part of the water molecule is facing an area where you have an oxygen sticking out. And where there might be a cluster of hydrogens, the water molecule will flip around so that its negative region will be attracted to those hydrogen molecules. So it's the same notion, it's just that it's happening over the area, surface area, or the outer regions of our molecule, that attraction between the positive regions and the negative regions. So when some materials dissolve in water, that gives water the capacity to conduct electricity. That usually means that you're going to have something like an ion in there, and those ions are going to allow a charge to flow through the fluid. And when we have materials like that dissolve in water and allow it to conduct a charge, we call those electrolytes. So sodium chloride is an electrolyte, a substance that dissolves into and creates ions in water is known as an electrolyte. So materials that dissolve in water to form a solution that will not conduct electricity are called non-electrolytes, and that would be an example of sugar in water. Water's ability to conduct electricity is not enhanced by putting sugar in it, but it is enhanced by putting salt in it. So just to reiterate what we talked about, when you drop sodium chloride into solution, the attractive forces of the water cause the sodium chloride ions to separate, and the water will flip around to put the appropriate charged portion of its molecule around that particular ion, whether it is the oxygen being attracted to the positively charged sodium, or whether it's the hydrogens of water being attracted to the negatively charged chloride ion. On the other hand, if you have a polar compound like sugar, which has areas of polarity as opposed to an outright polarity, then the water molecule will be attracted to those regions based upon the region and its polarity. So if you have a region where you have an oxygen poking out that's going to be negatively charged, the polarity of that region will be negative. If it's an area where you have a couple of hydrogen atoms attached to an oxygen, those who have a tendency to be slightly positively charged. So the water will flip around so that its oxygen will be oriented towards those positively charged hydrogens. So that's what's happening there with the dissolving of substances in water. So let's have another visit with electrolytes. So electrolytes are classified by how they dissolve in water. So these are substances that go into ions, that create ions when dissolved in water. So salt is an example of an electrolyte. In fact, things that do form those ions in water, I just have a tendency to generically call them salts, even if it's something like magnesium chloride or potassium bromide. They have a tendency to create ions in solution, so I classify them as electrolytes, and I think most sciences would. Now, depending upon their willingness to create ions in water, an electrolyte could be described as strong or weak. So if the dissociation of ions happens completely, as in the case of calcium chloride, we would say that this is a strong electrolyte. Now there are some weak electrolytes, such as our carboxylic acid here, and this is a kind of a molecule that you see attached to long chains of hydrocarbons usually, at least if you're studying the anatomically focused sciences or the physiologically focused sciences. The carboxylic acid end of a molecule is represented as CHOOH. And this has a tendency to dissociate and then reassociate. So it exists in an equilibrium. And as a result of it existing as in an equilibrium, that means that we're going to have part of the acid with the H attached and part of the acid with it being in its conjugated base state with no hydrogen attached. And in this way, it would be considered a weak electrolyte. Now, normally the ionic substances, such as sodium chloride or potassium bromide, are going to be strong electrolytes. And as we saw on the previous page, carbon, hydrogen, a couple of oxygens, and another hydrogen, that's not ionic, that is a molecular substance, and it will have a tendency to form a weak electrolyte. Now, we haven't talked much about acids and bases so far in this chapter. We will in a few more slides. But acids and bases are compounds. They're compounds, which means that they're molecules that when they dissolve in water, they will also go into ions. Typically, you're going to see it going into either an ion of hydrogen or an ion of hydroxide. And depending upon the acid or base, the dissociation can be either complete or partial, meaning that some acids and bases are strong acids and bases, and some are going to be weak. So for example, hydrochloric acid is a very strong acid. It completely dissociates in water. Acetic acid, which is basically what vinegar is a weak acid. And it dissociates only partially in water, which means that you will have some of the molecules of acetic acid in your solution, and you'll also have some free hydrogen ions and the acetate ion also present. So you'll have all three species present in a solution of acetic acid, which in this case makes it a weak electrolyte. So most molecular compounds, that is, things that are covalently bonded, and with the exception of acids and bases, molecular compounds dissolve in water as intact molecules. That means that you drop in a sugar molecule, you're getting a sugar molecule back out. And because they don't have the ability to break into their ion states or their ion constituents, that means that these are non-electrolyte solutions. All right, and this brings us to the end of part 1 of chapter 8.